morning and good day to all of you. My name is Najma Batar Mapandi. I am first year college under the course of BS Biology Section A. And now I'll going to show you my 3D model molecule or compound, namely the methyl 3 methyl pentanoate under my chemical biology subject. I'll going to explain to describe to you all about what is my molecule. So just sit back and relax and we will start and I'll start to explain to you. So I have here these 6 questions to be answered in order to illustrate with you and to discuss with you what test my molecule is all about. So let's start first for the question number 1, the introduction of my molecule, the methyl 3 methyl pentanoate, and what does its function to the snake fruit, so to the fruit that I have chose. So now I'm gonna show you the finished product of my 3D model compound molecule. So as you can see, this is the finished product of my molecule. So the name of this molecule is methyl 3 methyl pentanoate, and it was made up of recycled materials such as the stick, glaze, and the styrofoam. So this is my molecule. As you can see, the ball or the circle has the different sizes presenting the structure of this molecule. So this molecule, the methyl 3 methyl pentanoate, is responsible for the scent of the snake fruit. So the snake fruit is the fruit that I have chosen, and under this snake fruit is the methyl 3 methyl pentanoate, which is responsible for its odor or the scent. So this is my finished product. So this is it. So this molecule, the methyl 3 methyl pentanoate, is also known as the methyl valerate, which belongs to the class group of organic compounds known as the fatty acid methyl esters. So this methyl 3 methyl pentanoate is a very hydrophobic molecule, practically insoluble in water. In a very pure form, greater than 99.5%, this molecule is used in plasticizer in manufacturing a plastic. Methyl pentanoate is also commonly used in fragrances, beauty care, soap, and laundry detergents. It is also a flavoring agent. It is a sweet, apple, and fruity tasting compound. So this methyl pentanoate has been detected but not has been quantified in several different foods such as the tea, herbs and spices, alcoholic beverages, Asian pears, coffee, and coffee products. It is the ester formed by the condensation of the pentanoic acid, and it is a very hydrophobic molecule, like what I've said before, because practically it is insoluble in water and relatively neutral. So that is the introduction of my molecule, the methyl 3 methyl pentanoate. So what does the function of this molecule, the methyl 3 pentanoate, in the snake fruit? So the methyl 3 methyl pentanoate was regarded as the character impact odorant of the typical snake fruit aroma. The methyl esters of the carboxylic acids are characteristic of olfactory volatile compounds for the sweet aroma of the snake fruit. Although methanol was not detected as volatile constituent, the Good enzymes involved showed activity to synthesize the metal esters in the presence of the methanol. Therefore, the biosynthetic origin of the methanol was investigated, resulting in the detection of the pectin metal transferase activity in the flesh. This pectin metal transferase activity will increase during the fruit maturation. In parallel with the level of methanol originating from the hand-squeezed juice and with the methyl esters extracted from the flesh of the fruit. So that's for the question number 1. And now let's proceed to the question number 2. Explain the hybridization of each atom found in your molecule. So, when we say hybridization, it is the intermixing of atomic orbitals of the same energy level to form new degenerate orbitals. The new orbitals thus formed are known hybrid orbitals. So, the hybridization of this molecule, the metal tripentanoate, is tetrahedral. So when we say tetrahedral, the hybridization of 1s and 3p orbitals produce 4 hybrid orbitals oriented toward the points of a regular tetrahedron, having the 109.5 Celsius apart. CH3, or also known as methyl free radical, has a planar structure with sp2 hybridization of C atom. The odd electron is present in unhybridized 2pz orbital. These electrons corresponds to the 1s orbital and 2p orbitals as the electronic configuration of C in CH3. So, therefore, the CH3 will be equal to 1s to the power of 2, 2s to the power of 1, and 2p to the power of 4. Therefore, 1s and 2p orbitals of carbon combined overlap with s orbitals of 3 individual H atoms, resulting to the hybridization of sp3. Therefore, this molecule, the metal pentanoate, has the hybridization or resulted hybridization of sp3 or sp to the power of 3. So that is for the question number 2, and now let's proceed to the question number 3. Identify the functional groups in your molecule. So the metal 3-metal pentanoate is also known as the FEMA 2572 or methyl N-valerate, which belongs to the class of groups of organic compounds and to the functional group of fatty acid methyl ester. So the fatty acid methyl esters are compounds containing a fatty acid that is esterified with a methyl group. So they have the general structure wherein RC open parenthesis equals O and close parenthesis OR, wherein R equals to fatty alphatic tail or organelle group and R equals to methyl group. So the fatty acid methyl esters are used to produce detergents and biodiesel. In fact, most of the molecules in biodiesel are fatty acid methyl esters, usually obtained from vegetables oil by transesterification. And that is for the question number 3. And now let's proceed for the question number 4. If one or more atoms have formal charges not equal to 0, explain why. Each hydrogen atom is formally neutral. they get one electron from each covalent bond, and the carbon also gets one electron from each covalent bond, resulting to have a two inner core and electrons. So, the carbon has these 5 electronic charges, but not necessarily 6 positive nuclear changes. So, the formal charges will be equivalent to positive 1. Just to add this in the purposes of assigning a formal charges. In covalent bond, electrons are shared between the nuclei. An ionic bond is between a formal anion and a formal cation, and thus involves a prior. In transferring of electron, if we take say methane with 4 CH bonds, we split this up to keep 4 times H bonds, and the carbon atom with 4 valence electrons. The hydrogen atoms are neutral because they have a positive nuclear charge and also an electronic charge, and hence the hydrogens are also neutral. Likewise to the carbon atom, claims 4 electrons from the 4 CH bonds and has 2 inner core electrons. And so, each carbon has 6 electrons and there are 6 positive nuclear charges. Thus, the carbon atom in metal 3 metal pentanoate is also thus electronically neutral. So that is for the question number 4. And now let's proceed to the question number 5. Explain the molecular orientation and shape of at least 3 atoms with different orientation and shapes. Molecules have different shapes. There is an abundance of experimental evidence to that effect, from their physical properties to their chemical reactivity. Small molecules with a single atom have shapes that can be easily predicted. Some of the most common shapes that can be taken are linear, tetrahedral, trigonal planar, pyramidal, and angular or bent. The molecule that is made up of 4 equally spaced sp3 hybrid orbitals forming bond angles of approximately 105.9. The shape of the orbitals is tetrahedral. I'm going to explain at least 3 atoms, namely the methane, carbon, and the water that can be found in my molecule metal 3 metal pentanoate. So let's begin first with the first atom, namely the methane. Methane is an organic compound that is the primary component of natural gas. Its structure consists of a central carbon atom with 4 angle bond to hydrogen atoms. In order to maximize their distance from one another, the 4 groups of bonding electrons do not lie in the same plane. Instead, each of the hydrogen atoms lies at the corner or at the center of a geometrical shape called a tetrahedron. The carbon atom is at the center of the tetrahedron. Each face of a tetrahedron is an equilateral triangle. The molecular geometry of the methane molecule is also called as the tetrahedral. So now let's proceed for the second atom, the H2O, or also known as the water. A water molecule consists of 2 bonding pairs and 2 lone pairs. As for methane and ammonia, the domain geometry for a molecule with 4 electron pairs is tetrahedral. In the water molecule, 2 of the electron pairs are lone pairs rather than bonding pairs. The molecular geometry of the water molecule is bent. The HOH bond angle is 104.5 degree, which is smaller than the bond angle in nitrogen. And now let's proceed to the last atom, the carbon. Living things are carbon-based because carbon plays such a prominent role in the chemistry of living things. This means that carbon atoms bonded to other carbon atoms or other elements form the fundamental components of many, if not most, of the molecules found uniquely in living things. The 4 covalent bonding positions of the carbon atom can give rise to a wide diversity of compounds with many functions. accounting for the importance of carbon leaving things. Carbon consists 4 electrons in its outer shell. Therefore, it can form 4 covalent bonds with other atoms of molecules. The simplest organic carbon molecule is methane, CH3, in which 4 hydrogen atoms bind to a carbon hydrogen. However, structures that are more complex are made using carbon. Any of the hydrogen atoms can be replaced with another carbon atoms covalently, bonded to the first carbon atoms. In this way, long and branching chains of carbon compounds can be made. The carbon atoms may bond with atoms of other elements such as nitrogen, oxygen, and phosphorus. That is for the question number 5. And now let's proceed to the question number 6, the last but not the least. Explain the polarity of the molecules based on bonds between atoms and dipole moments of the molecule. So the dipole moments occur when there is a separation of charges. They can occur between two ions in an ionic bond or between atoms in a covalent bond. When atoms in a molecule share electrons unequally, they create what is called a dipole moment. This occurs when one atom is more electronegative than another, resulting in that atom pulling more tightly on the shared pair of electrons, or when one atom has a lone pair of electrons and the difference of electronegativity vector points in the same way. In fact, one of the most common examples is the water molecule, made up of 1 oxygen and 2 hydrogen atoms. The metal 3-methylpentanoate, having the formula of C6H12 and O2, is nonpolar both within each bond and in an overall molecule. Polarity can either be within a bond when one atom hugs the electrons more than the other, or in the overall molecule when all the electrons tend to group one or to one side of the molecule but not on the other. A dipole simply refers to the two poles of a magnet. Similar to that, a chemical bond with a dipole suggests that one atom is partially negative and the other is partially positive. Since each individual bond is not a polar, we don't expect the molecule as a whole to be polar. Let's pretend that each bond is polar enough to be polar, though even then the C6H12, or also known as the methylpentanoate, has no lone pairs. And that is good sign that this molecule is symmetrical. So due to the properties of vectors, we have this 3 statement to remember. So first is the bottom 2 arrows add downwards and cancel out horizontally along the plane of the screen. Second, the top 2 arrows add upwards and cancel out horizontally perpendicular to the plane of the screen. And lastly, since they were all the same vertical magnitude to begin with, the up and down arrow sums cancel out as well. The net dipole moment of the metal 3-methylpentanoate or C6H12O2 is 0, meaning that the molecule is nonpolar by its symmetry. So that will be the end of my video presentation under my chemical biology subject. So once again, my name is Najma Batar Mapandi, first year college from BS Biology Section A. Have a good day and keep safe always. Goodbye!